Hi, welcome to problem 4. In this problem, you're asked to apply the RSA algorithm to a situation and help the people in the situation have better security. Well, the one thing that should pop up to you is, well, you won't be able to meet each other until the day, so that means we have to enforce security through the messages themselves rather than through eyewitnessing. So security through messages. What else do you see? Well, if you look at the friend's scheme, he asks you to toss a coin and tell him, but then what can he do after you tell him? He decides. So this other person, right, friend, has imbalance of power. So he can make a decision of what to do with your response in addition to what he's tossing. So can make more decisions. So clearly there's something wrong with this scheme, and the thing that's wrong is that the person who sends the text first is pretty much powerless, right? So if I send a text to my friend, how can I make sure that this text is secure? How can sender make sure message is secure? And in problem 1, it's clear that the problem is that the friend, the receiver, can see the response and change his or her decision based on that, which is not good because that puts the receiver at such a big advantage. So then we need to think of some integrity constraints. These are basically just little reminders for what your security system must follow. So one security constraint then is that the sender needs to know that his or her choice won't be leaked. And how do you think you should go about this goal? Well, the obvious answer is encrypt the message. And we'll see how to do that in a moment. But now that the sender wants to know that his or her answer won't be revealed, the receiver, and this is a new complication from the solution in 1, the receiver needs to know that the sender is being honest. Sender's answer is truthful. How can you, so basically this boils down to a question of how to verify if you can't see the answer. And there are 2 ways to go about it, right? You can either decrypt, or you can compare with something else. And we'll see that the second answer is much better for our security purposes. And finally, keys should not be shared. Private keys should not be shared. And this is to ensure that any further transactions can proceed without a new key being sent every time, because how are you going to generate those keys every time? Anyway, I'll go into public key cryptography really quickly and discuss how public key cryptography helps with solving our security constraints. And this is via the RSA. So yeah. All right, so in public key cryptography, you are expected to broadcast messages freely. And there's a public key to do so. And you wonder why this is even secure. Well, notice that when you send a message, right, the receiver also has to receive the message. So this is a 2-part process. And the security lies in the receive part, where you can only decode if you have the private key. Decryption only with private key. So that is the main gist of public key cryptography. Decryption is the secure part. So now we look back to our integrity constraints and see, how does public key cryptography help? Well, the sender needs to know his or her choice won't be leaked, so you encrypt the message. That's exactly what you can do here. You can encrypt the broadcast message. Now the receiver needs to know that the sender's answer is truthful. Well, we don't want to give away how we encrypted an answer to decrypting our encrypted message, because that defeats the purpose, right? So the only option is to compare with something else. And what can you compare an encrypted message with? Well, the one thing you can compare with is the original message, right? The unencrypted. So compare encrypted with unencrypted. All right. Pause for a moment for you to write everything down. Now, the best way to approach number 2 is to draw the model again. And we know from answering our integrity constraints that we want an encrypted message. Now, in RSA, the way you encrypt messages, you have to choose. So step 1 is choose public and private key to encrypt message. Now, once the receiver receives the message, the receiver expects to be able to compare it some other time. But it's not really important right now. The receiver can send his or her own encrypted message. I'll call this encrypted A, encrypted B message. And now what can the sender do again? Well, the sender knows that the sender already sent an encrypted message, so to compare and make sure that, to comply with truthfulness, the sender is going to send an unencrypted, right? Because we talked about the fact that the receiver must be able to compare. And what does the receiver need to know in order to compare? Well, the receiver has to know the public key. Because then you have unencrypted public key to an encrypted message, and then you do the comparison. Sorry for the cramped handwriting. And then the friend does the same. And that is the general scheme for 4.2. And then, so then we just have to write this down more formally. So I choose a public and private key to encrypt message. I send the public key and the message. I keep the private key. That's the important part. The friend receives the encrypted and saves it, then does step 1 to me. And then now, what do I get to do? I have to send the unencrypted for verification. And then now the friend can verify. To make sure we've done it right. And then the last step is also for the original person to verify. Now you can see how this can be done with RSA, and basically you just have to replace the private key with D and the public key with N and E, right? This is algorithm specific. And then And then encryption and decryption is just the raising the power. So as mentioned in the solutions, the sender is not at a disadvantage because the receiver cannot see my response. Meanwhile, the receiver is not at a disadvantage because the sender already commits to an answer and cannot do anything else. So that is how our security is enforced and how everyone has an equal balance of power. So that is how you do problem part 2. Now for part 3, we build upon the subtlety presented in part 2 where it's possible, where you can understand the contents of a message without decrypting it. And how do you go about doing it? Well, it's a 2-step procedure. The first step is you must receive an unencrypted form of the message. And the second thing is you use the public key to encrypt the message in one and compare it with the encrypted message you received earlier. Now going back to our original framework of Alice sending an encrypted message to Bob, notice that we send an encrypted message and we also send a public key. And similarly, encrypted and then we send an unencrypted. Now the critical step is, can Bob figure out Alice's encrypted message before the unencrypted arrives? And that is the problem that problem 3 points out, is that if you only choose out of heads or tails, your encrypted message will be just fine. It's either heads or tails, but Bob can just use the public key and guess his own set of messages to encrypt, and this will pretty much give you the same result. And guessing gets Bob through number 1, and so he can learn Alice's answer. So what is the solution to prevent this guessing from happening? Well, the solution is to make it unguessable. And the best way to do that is by randomizing the set of possible messages. Now remember that we still have to follow the constraint that the encrypted must be equal to unencrypted plus transformation by public key. So the sender, however, has access to send both of these, and so the sender just has to make sure sender chooses random prefix or suffix and stays consistent. In the solutions, this is known as a salt. So random prefix suffix is equal to a salt. And so you use the salt to randomize the pool such that it makes it unguessable for Bob, but Bob can still verify it once he receives the unencrypted message. And so that is the solution to part 3. Now we are on to part 4. in part 4, we see that we have an n greater than or equal to 2, and people have to be whole. So n whole and greater than equal to 2. This makes it a perfect candidate for induction. So we need an inductive proof to prove that this scheme will work for multiple people. Now let's consider the simple case where we have Alice and Bob. So n equals 2 works very well because of this procedure we've established. Now what happens when we add a third person, Carmen? Well, we can already build from the fact that Alice and Bob will both be truthful. But someone has to tell Carmen what the results of their coin tosses are. So we can choose Alice or Bob to report results to Carmen. Meanwhile, Carmen has to report results. Reports own result. So here, while this this channel is secure between Alice and Bob, the channel between Alice, Bob, and Carmen is not necessarily secure until we establish RSA for those two. But you can see that the procedure is pretty much the same because we're building this inductively. And so each step along the way should have a similar buildup. And the way to do this is, of course, Bob encrypts the result from the n people tossing the coin, which we can assume to be true from the inductive hypothesis. Now what's next? So Bob encrypts, sends to Carmen, and Carmen encrypts her own result, send back to Bob. And you can see how this is very similar to problem 2, where Bob would just send unencrypted results, and so forth. And so you can see that this is extremely similar to problem 2. The only thing we added is this inductive hypothesis. Problem 2 serves as our base case, and our inductive step is just one more communication channel that has to be secured via RSA. But that is the basic idea. And there's some implementation details that you can pay attention to, such as using XOR. You can encode information easily with XOR, but the main idea is you can extend inductively because communication is two-way, and once you secure two people's communication, they become one, and then you can use that unit to communicate with the next person and build up inductively from there. So yeah, that is problem 4 and the last problem of this homework, besides the midterm questions.